Hello and welcome to ControllersTech. In today's session, we will continue with the STM32 IoT series using the ESP8266 Wi-Fi transceiver module. In the previous video, we learned how to connect the STM32 to the ESP8266 module, how to configure the UART, and finally how to connect both the module and the board to a Wi-Fi network. We will now continue from that point. In this video, our focus will be on sending data to a cloud server, specifically using ThingSpeak. For this demonstration, I will use the BME280 sensor to measure temperature, pressure, and humidity. Once we capture these values, we will upload them to the ThingSpeak cloud. If you haven't watched the first part of this series, I strongly recommend watching it first, because in this video I will assume that your STM32 is already connected to the internet. Now, before we dive into coding and uploading data, let's first set up a channel on ThingSpeak. Start by opening the website, thingspeak.mathworks.com. Click on the Get Started for Free button. If you don't already have an account, you'll need to create one here. Since I already have an account, I will simply log in. You can see that I already have one channel here, which I was using for testing purposes. But let's go ahead and create a new channel by clicking on New Channel. Give your channel a meaningful name, for example, STM32 ESP8266. Next, we need to enable the fields for this channel. Think of these fields as columns in a table. This is where your sensor data will be stored. Since I want to display three values, temperature, pressure, and humidity, I will enable three fields. You can also rename each field to match the parameter it represents. Leave the other settings at their default values, and then click Save Channel to create it. Once the channel is created, you will immediately see three charts, one for each of the fields we enabled. ThingSpeak also allows you to add widgets like gauges, numeric displays, lamps, or even image displays, to make your dashboard more interactive. For example, let's add a gauge widget. This gauge needs to be linked to one of the fields we defined earlier, so I'll connect it to the temperature field. Here, you can adjust parameters like the minimum and maximum values, the measurement unit, and even define a warning range using the red zone. By default, the update interval is set to 15 seconds, and that's also the minimum allowed in the free version of ThingSpeak. This means you cannot push new data more frequently than once every 15 seconds. Now, you can see that our gauge is displaying correctly according to the settings we just configured. You can also make your channel available for public viewing by changing the sharing settings. Go to the Settings tab if you want to edit channel information such as its name, description, or fields. In the Sharing tab, you can either share the channel with specific email addresses or simply make it public. Once shared, the charts and widgets you created will also be visible publicly, as you can see here. The next important step is the API keys section. This is one of the most critical parts of ThingSpeak. API keys allow you to either write data to your channel or read data from it. For writing data, you will use the write API key. The request includes the key itself, the field you want to update, and the value to be stored. We'll take a closer look at how this API request works in just a moment. Before we begin writing the main project, let's first test the AT commands using a serial terminal. For this test, I have connected the ESP8266 module directly to a USB to TTL converter, such as the FD232. The converter is then connected to the computer through a USB cable. The wiring is simple. The TX pin of the ESP module goes to the RX pin of the converter, and the RX pin of the module connects to the TX pin of the converter. As we already established in the previous video, the ESP8266 communicates at a baud rate of 11.5200. So, make sure you open the serial terminal with the same baud rate. Also, remember to add a carriage return and line feed at the end of each command you send. Now, let's begin by sending a basic AT command. The module responds with OK, which confirms that everything is working fine. Next, let's restart the module once. After restarting, the ESP8266 connects automatically to the Wi-Fi network that we configured earlier. This happens because the module stores the Wi-Fi credentials in its flash memory, so you don't need to re-enter them every time. Now that the module is connected to the Wi-Fi, we can move ahead and test a new set of commands. I have already prepared the commands we will use for this demonstration. Let's begin with the SIP start command. This command allows us to create either a TCP or UDP connection to a remote server. In this case, we will establish a TCP connection with api.thingspeak.com. We will use port 80, which is the standard port for HTTP requests. While this connection is unsecured, it is much simpler and perfectly suitable for our project. When we send this command, the ESP8266 responds with connect followed by OK. This response is very important because, in our actual code, we will rely on it to confirm and automate the connection process. The next step is to send the SIP send command, where we specify the number of bytes of data that will be transmitted in the following request. Here, I am instructing the ESP8266 module that I will be sending 68 bytes of data after this command. The module responds with a greater than symbol, which means it is ready to receive the 68 bytes. Next, we send the right channel feed command for ThingSpeak. It is important to insert the right API key at the correct position in this command. This command itself contains 66 characters, including the spaces. The remaining 2 characters are the carriage return and line feed, which make the total length exactly 68 bytes. Once the ESP module receives this data, it transmits it to the remote server, in this case, the ThingSpeak server. The server, in turn, sends back a response to the module. This incoming data is displayed on the console as IPE packets. In this particular case, the server sent back just 1 byte of data, which is the number 1. This number is very significant because it represents the entry ID or update ID. In other words, it tells us how many updates have been made to the channel so far. Finally, the TCP connection is closed, either by the ThingSpeak server or by the ESP8266 module itself. Now, let's go back and check the ThingSpeak channel. As you can see, all the fields have successfully received the values we just transmitted. The gauge widget is also showing the temperature reading correctly. Let's try sending another set of values. Just like before, we need to start from the beginning and send all the commands again. This time, I'll set different values for all 3 fields. Since I'm using 2-digit values again, the length of the command remains the same. After sending the command, we receive another success message from the server. This time, the entry ID is 2, which means the second update to the channel has been completed. If we check the channel now, we can see the new set of data has been successfully updated in all 3 fields. This demonstrates how we can send data to the ThingSpeak server. The next step is to automate this entire process in our STM32 code. Along with the ESP8266, I am also using the BME280 sensor with its library files. I have already explained how the BME280 sensor works with STM32 in a separate video. If you haven't watched that yet, you can check it out from the link in the top right corner. The BME280 library files are actually part of this project itself. Once you download the project, you can find these files inside the source and include folders. Simply extract them from there, so we can include them in our STM32 project. Now let's start setting up the project. I am going to continue with the same project we created in the previous video. However, I will rename it as Part 2 for better organization. While renaming, make sure to select the Update Reference option. This ensures that all project references from Part 1 are updated to Part 2 correctly. Alright, the renaming process is complete. Everything has been updated to Part 2, except for the debug configuration. Let's delete this debug configuration along with the debug folder. Don't worry, these will be regenerated automatically once we launch the debug process again. Next, we need to add I2C functionality so that the BME280 sensor can communicate with the STM32. Open the CubeMX file, and configure I2C1 for this purpose. Here, pins PB6 and PB7 are assigned as the I2C clock and data pins. We will look at the exact wiring and pin connections in just a moment. The I2C configuration is kept at its default settings, which means we are using the standard mode with a 100 kHz clock for the BME280 sensor. Now, let's regenerate the project. Since we need new functions, delete the old ESP8266 library files from the previous project. After that, copy the updated library files into the project, place the source files inside the source directory and the header files inside the include directory. Let's take a look at what has changed inside the ESP8266 source file. The first few functions remain the same as in our earlier project. However, I have added a new function called Send to ThingSpeak, which will handle sending sensor data to the cloud server. Now, you might notice a float formatting error inside this function. This happens because we are trying to convert a floating point value into character format using printf. To fix this, right-click on the project and open Project Properties. Go to C++ Build Settings. Under MCU/MPU Settings, enable the option to use float with printf. Click Apply and Close, and this error will disappear. Now let's understand what the Send to ThingSpeak function actually does. The parameters of this function are the ThingSpeak write API key and 3 float values for the 3 data fields. If you plan to use fewer than 3 fields, or more than 3 fields, you can easily modify the function parameters accordingly. The function begins by sending the SIP start command to establish a connection with the ThingSpeak API server. After that, it waits for the connect response from the ESP8266 module. We saw this behavior earlier during the AT command testing. Once the connection is confirmed, the function constructs the channel's write feed URL and stores it in a buffer. This URL contains the API key along with the values passed to the function as parameters. If you don't want to use all 3 fields, you can modify this URL. For example, to remove field 3, simply delete that portion from the URL. To use only one field, remove both field 2 and field 3. Remember that the carriage return and line feed characters are also included in the URL. Their length is calculated before transmitting the URL to the module. Once the URL is prepared, the function sends the SIP send command, which specifies how many bytes of data will be transmitted next. After sending this command, the function waits for the greater than symbol, which confirms that the ESP8266 is ready to receive the data. Next, it sends the URL itself and then waits for the send OK response from the module. However, there's something important to note: the ESP8266 may return send OK even if it receives an incorrect number of bytes. That's why, to confirm that the data actually reached ThingSpeak, we must also check for the +IPE response. From this response, we can extract the entry ID, update ID, which appears after the colon. Receiving this ID confirms that ThingSpeak has acknowledged and stored the data we sent. That's all the changes I made to the ESP8266 source file. Now, let's quickly move to the BME280 source file. Here, the main function of interest is the BME280 config function. This function configures the BME280 registers, and initializes the sensor. I have already explained this in detail in my BME280 article and video, so for now, we will simply use the same initialization code from there. Alright, with that covered, let's move on and start writing the actual code. First, include the BME280 header file along with the ESP8266 header file. Inside the main function, once the ESP8266 successfully connects to Wi-Fi, call the BME280 config function to initialize the sensor. Next, define 3 float variables to store the values of temperature, pressure, and humidity. Inside the while loop, call the BME280 measure function to measure and update these variables with the latest sensor readings. Before sending this data to the ThingSpeak server, we need to confirm that the ESP8266 is still connected to Wi-Fi. The enumeration ESP8266 connection state defines all possible connection states of the ESP8266. In the ESP8266 source file, there is a variable called ESPConState, which holds the current connection state. So, inside the loop, we will check if the ESP8266 is connected and has an IP address. If the connection is active, then we will call the function ESPSend to ThingSpeak and pass the temperature, pressure, and humidity values to it. Make sure to add a delay of at least 15 seconds before sending the next set of data. As I mentioned earlier, ThingSpeak's free accounts require a minimum interval of 15 seconds between updates. We also need to pass the channel write API key to the function. So, let's define this key as a variable in the code. Now pass this key to the ThingSpeak function call along with the sensor values. Alright, let's build the project now. The build completed successfully with no errors, so we're ready to flash the code onto the STM32 board. Before we do that, let's quickly review the hardware connections. The ESP8266 wiring with STM32 was already explained in detail in the previous video, but let's go over it again. The RX pin of the ESP8266 connects to PA0, UART4TX, of STM32. The TX pin of the module connects to PA1, UART4RX. I am using an ESP adapter, which is powered with 5 volts from the STM32 board itself. If you plan to connect the ESP module directly without the adapter, you can refer to the connection diagram in the article linked in the description. Now, let's look at the BME280 connections. The BME280 is connected via I2C1. The data pin, SDI or SDA, of the sensor connects to PD6, I2C1 SDA, on STM32. The clock pin, SCK, of the sensor connects to PB7, I2C1 SCL. One important note, if your BME280 module also supports SPI mode, like the one shown in the image, you must connect the SDO pin to GND. Otherwise, the I2C slave address will change. If your module only supports I2C, you can ignore the SDO pin and simply connect SDA to SDA and SCL to SCL. The BME280 is powered using 3.3 volts from the STM32 MCU. In addition to the ESP8266 and BME280 modules, I have also connected a USB to TTL converter, FD232, so we can view logs in the console. This is connected through UART1, where the TX pin of the MCU is connected to the RX pin of the converter. That's all for the hardware setup. Now, let's head over to the ThingSpeak channel settings and clear the channel before we start logging new data. Clearing the channel will remove all the test data we sent earlier. As you can see, the channel has now been cleared. Let's go back to the project and flash the firmware to the board. Now, let's open the serial console and observe the logs. I have only enabled user logs, so the output stays clean and minimal. As you can see, the ESP8266 has been initialized, and it is now connecting to the Wi-Fi network. After connecting, the module waits until an IP address is assigned. Once the IP address is obtained, the module immediately sends the data to the ThingSpeak server. If the data is received correctly by ThingSpeak, the server responds with an entry ID, also called update ID. This ID is then printed on the console. This confirms that the data has been successfully logged to the ThingSpeak channel. After a 15-second delay, another set of data is sent. If the update is successful, you will see the entry ID increase by 1 each time. Now, let's check the ThingSpeak channel. We can clearly see 2 values under each field. The temperature values look correct, but notice that the pressure values are being sent in pascals. To make them easier to read, let's modify the main function so that the pressure is reported in kilopascals instead. Rebuild and flash the project again. We need to clear the channel once more, otherwise the chart will look odd, switching from values like 94,000 to 94 after the change. Now I'll fast forward the video so you can watch the updates happening in real time. With every update, ThingSpeak returns an incremented entry ID, which shows the total number of updates sent to the channel so far. To make the dashboard more meaningful, we can also update the titles of the charts so they clearly show what each field represents. Now everything is working as expected. The STM32 successfully measures the current temperature, pressure, and humidity using the BME280 sensor, and the ESP8266 uploads these readings to the ThingSpeak cloud. With that, we have successfully completed part 2 of this IoT series. In the next video, we will move forward and implement MQTT client functionality. In that setup, the STM32 along with the ESP8266 will act as an MQTT client, which will be able to both subscribe to topics and publish messages. We will also explore how to use the received data in a practical way, for example, by controlling an LED or displaying the values on an LCD. That brings us to the end of this video. If you'd like to read the full article and download the project files, you'll find the link in the description below. Feel free to leave a comment if you have any questions or doubts. Thank you for watching, and have a great day ahead.